So in terms of questions that we're trying to answer here, I want to find all the equilibria. And I know that's messy, hard to read, but I want to find all the equilibria. I want to draw the phase plot. And I also want to use the local stability criterion. And then for some specific starting values of P, I want to look at what the limit as T approaches infinity of P will be for some specific starting values. So here's my equation. And if I have to find the equilibria, anytime we're being asked to find equilibria, that means we're going to set that differential equal to 0. This one happens to already be factored for us because I have a P times a 1 minus P times this chunk in here. For problem 3 on the homework, you're going to have to do the factoring yourself. So you can either multiply it all out first and then factor it, or factor it from where it starts. But here it's already factored for us. So I know that I'd have P is equal to 0, P is equal to 1, or this whole thing is equal to 0. So 1 minus P minus 2P is equal to 0. Looks like that's a minus 3P, so 1 is equal to 3P, P is equal to 1/3. So my 3 equilibria here are at 0, 1, and 1/3. Those are my equilibria. Check. Now in terms of the phase plot, we have options. I'm pretty good at graphing, so I would just graph the thing. But we can also turn to our friend Desmos. So here's our graph. And to turn this into a phase plot, what I need to show is what direction each of our values, what direction we're getting pushed for different initial conditions of P. And we've been talking about this for, at least we were doing a bunch of these on Monday and some of this on Friday also. Anytime I'm above the axis, so any region where the curve is above the axis, those are places where I would be pushed to the right. And anywhere that we are below the axis, those are places where we'd be pushed to the left. So I've got my phase plot, and now I can say something about the stability. So the equilibrium of 0, all of the arrows on my phase plot are heading away from it, which means 0 is an unstable equilibrium. So 0 is unstable. 1 is also a place where all of my arrows are heading away from it. So 1 is also unstable. But 1/3, all of the arrows are pushing in towards 1/3. So this is my stable equilibrium. So that's the information that I can get from this phase plot. But what about the local stability criterion? So the local stability criterion, that's the one where we're going to end up taking the derivative of our function and plugging the equilibria into it. Well, I don't know about you, but I do not want to do a triple product rule. So if I'm going to have to take a derivative of this, right, if I call this f of p, and I'm going to have to find that derivative, I personally want to multiply this stuff out, which is also an option for problem 3 in the homework instead of a phase plot, because for question 3, he didn't tell you that you had to use the phase plot. He just told you that you had to come up with the stability. So you can do that using the local stability criterion. So if I start multiplying this out, then here, when I distribute the p in, I will have p minus p squared. Over here, if I clean it up, I don't really need those parentheses, and the minus p minus 2p is going to make this 1 minus 3p. So we could choose to do a product rule from there or keep multiplying. I'm going to keep multiplying. So I'll have p minus 3p squared minus another p squared plus 3p cubed. So to recap that, that means that my f of p, which was p prime, when I multiplied everything out, it worked out to 3p cubed minus 4p squared plus p. So when we do that local stability criterion, what we're really looking for is on this curve, is my slope positive as I go through the equilibrium or negative as we go through the equilibrium? So I need to come to this equation and take another derivative. So I'll have f prime of p. So here I'll get 9p squared minus 8p plus 1. And then we're going to check at each of our equilibria, what's the value of this f prime. So at 0, when I do that f prime of 0, I'll have 9 times 0 squared minus 8 times 0, I'll get 1. Because that's positive, I know this is unstable, which matches what we got from using the phase plot. If I look at f prime of 1, I'm going to get 9 minus 8 plus 1, which is also greater than 0, so it's also unstable, which is what we got. And now we get to have fun with fractions. So f prime of 1/3 would be 9 times 1/3 squared, but 1/3 squared is 1/9, and 9 times 1/9 is 1, minus 8/3 plus 1. Okay, I don't actually need to do the arithmetic here. I just need to know if it's positive or negative. Adding those two ones together, that would be 2 or 6/3, and that negative 8/3 is going to be bigger. So I know overall that's negative, so it's stable, which also matches what we have here. Now for the last part of this question, I didn't actually write this out in words, but let's pretend that we were answering the same question as the way that it is phrased in number 3 of the homework. So I'm going to need to erase something here to write some words out. I can erase this. Sure. So what this says is find the limit as t approaches infinity. And in the homework problem, it's n. Here we're talking about p, so I'll use p of t, depending on the initial condition. And for that problem, he gave us an initial condition that n of 0 was greater than 0. I'm going to make up an initial condition here, and I'm going to say that our initial condition that I want to look at here is for p less than 1/3, but greater than 0. I think it's easiest to answer the question about the limit by looking at the graph. This is telling me that I'm starting with an initial condition somewhere in here between 0 and 1/3. And no matter where I start in that initial window, I'm going to get pushed over here to 1/3, which means the limit as t approaches infinity of p is equal to 1/3 as long as our p naught was between 0 and 1/3. So if our initial condition, if we start off in this window, then in the long run, we're just going to follow those arrows towards whatever point we're headed to. Now, for a different initial condition, let's say that we were given an initial condition that P naught is greater than 1. Well, now I'm starting over here, somewhere bigger than 1, and all of those arrows are moving away from 1, which means that after a really long time, my P is headed to positive infinity because there isn't anything that's going to make us stop. If my initial condition had been that P naught, or P of 0, was between 1/3 and 1. So now I'm starting somewhere in here between 1/3 and 1. Those arrows are pushing me towards the 1/3, which means the limit as t approaches infinity would be equal to 1/3. And that statement that it will depend on A just means that A is going to be in our answer when we go to find the equilibria. So looking at this, finding equilibria, I'm going to set that y prime equal to 0. And if this says 0 is equal to y squared minus a over y plus 1, and I already know that y is greater than -1, so I don't have to worry about dividing by 0 here. If this is equal to 0, then I don't actually care about the denominator. I just care about that y squared minus a being equal to 0. What that tells me, if y squared minus a is equal to 0, I can add the a over to the other side, and I'm going to get that y is equal to plus or minus the square root of a. So I have potentially two equilibria. But there's one value of a where I would only have one equilibrium, and that would be if a was equal to 0. So looking at this algebraically, if a is a negative number, then the top part has no solutions, because y squared plus something is never going to, like plus a positive number, is never going to equal 0. So I know for sure that in order to be looking at anything, my a has to be positive. So I know my a has to be bigger than 0. And we also saw in the picture that something interesting happens when a is equal to 1. And if we look at this equation, we can kind of see why something interesting happens at 1. So if the top said y squared minus 1 over y plus 1, then that top would actually factor as y minus 1 times y plus 1 all over y plus 1. And that would go away, and this would just look like y equals 1. So again, we wouldn't have two solutions. We'd really only have one equilibrium at that point. So when a is between 0 and 1, we have one type of thing happening in terms of the stability. And when a is equal to 1, we have something happening in terms of the stability. And then when a is greater than 1, we have something happening in terms of the stability. So if we're determining whether these equilibria are stable or unstable, we're going to have to consider all three of these cases. I already wrote this out for the A equals 1 case. So let's just finish that off. So when this is my A equals 1 case right here, and if A is equal to 1, then this is what our y prime equation simplifies to just be y minus 1, which would mean that y equals 1 is the only equilibrium. And then in terms of stable or unstable, I might as well just graph this because that's the equation of a line. I know how to graph a line. So for A equals 1, this graph would look like, well, that's got an intercept of -1 and a slope of +1. And there's my 1 equilibrium. Everywhere above the axis, I know my arrows should move to the right in terms of that phase plot, and everywhere below the axis, my arrows should move to the left. So for 1, that's an unstable equilibrium because all the arrows are kind of running away from it. So y equals 1 is an unstable equilibrium. Now let's look at the other cases. So if A is greater than 0, let's look at that case, or sorry, greater than 1. So let's investigate the A is greater than 1 case. And if A is greater than 1, we know that the equilibria are going to be negative square root of A and positive square root of A. Now we have a choice. We could think about doing this graphically, or we can use the stability criterion. Doesn't really matter, but my guess is most people are less comfortable graphing this than taking the derivative of this. So I'm going to go ahead and use the stability criterion here. I also want to point out that if A is, well, no, we'll go back. We'll deal with that in a second. So we know that y is greater than -1. And if I call this f of y, and we go to take the derivative, I'm looking at a little bit of quotient rule. So the derivative of the top, I would get 2y, and then we'd multiply that by the bottom. Plus, we leave the top alone and multiply by the derivative of the bottom, which is 1. All divided by y plus 1 squared. That may look terrible, and it is. I gotta erase my words so that I've got more space to do math. It may look terrible, and it is, but remember, all we care about in terms of the stability criterion are when we plug these points in, do we get a positive number or a negative number? That's it. I'm going to go ahead and multiply that out on the top. So I'll have 2y squared plus 2y plus y squared minus a, and the bottom, y plus 1 whole thing squared. So on the top, that's 3y squared plus 2y minus a all over y plus 1 squared. Okay, now back to here. So if I'm going to decide whether these points are stable or unstable, I'm going to plug that square root of a in everywhere we see a y. But I only care about whether this thing is positive or negative. The bottom, I don't care what we plug in, we're squaring it. It's always positive. So I really just have to focus in on the top. So if I plug in the square root of a for y, then that f prime of the square root of a looks like 3 square root of a squared. It's going to bring me back around to 3a plus 2 square root of a minus a. 3a minus a is going to be 2a plus 2 square root of a. Well, whatever that is, it's got to be positive. Because the square root of a is some positive number, and we know that a is greater than 1. So this means that that equilibrium is unstable. Also, if a is bigger than 1, I don't actually have to consider this other equilibrium because we know that we need y to be greater than -1. So if a is bigger than 1, this equilibrium is outside of the domain we were worried about. So we took care of when a equals 1, and we took care of when a is greater than 1. So the only other thing that could happen is that a is between 0 and 1. So if a is between 0 and 1, then we're still kind of back to this same equation. But knowing that a is between 0 and 1, oh wait, if a is between 0 and 1, that square root of a is still going to lead me to an unstable equilibrium. So it looks like no matter what we do, this equilibrium is going to be unstable. But we still had to consider the 3 separate cases depending on the value of a.